I want to spend a few minutes just to tee up this conference. The first concept that I would introduce to you, which is one with which you are well familiar, is that the times they are changing. Thomas Friedman, who wrote a Pulitzer Prize-winning book called The World is Flat, where he tried to make the argument that economics and communications had reduced barriers to such an extent that they were essentially non-existent, and that people were everybody was everybody's neighbor, and that there was some eventual point of equality that was going to take place. We were all linked arms and walk gaily into the future together. But the reality of the situation is the world is a very disparate place, and the world is separated by a large number of things, not the least of which is wealth. And this chart over here is a world grabber map which shows proportionately the amount of wealth in each geographic division, and you see, not surprisingly, that there's no major change expected over the next 3 to 4 years in terms of the distribution of wealth. And in fact, this is one of the great levelers that we deal with. And just for your edification here, the changes that are expected are really a shift to the east, where in terms of territory, that is wealth per unit space, not wealth per unit person, but wealth per unit space, there's a remarkable shift to the east, whereas the poorest of the poor remain poorest of the poor. Now, here in the United States, we have a slightly different worldview, which is that there we somehow still have this great agrarian democracy with a large fence built around it that keeps out disease and alien thoughts. On the other hand, I think most of us would agree that this is a primitive, at best, worldview, and things are changing, certainly in that way. The second concept that we all deal with is this notion of the academic silo. This is actually, this is not photoshopped. This is taken from a farm silo out in Portland, Oregon. And it emphasizes the fact that silos, those vertical divisions, do promote concrete thinking. And one of the themes and major goals of this conference is to change that notion of silo and to understand that with a common language and common problems, we can find common solutions. Edward O. Wilson, a professor, he's a lifer at Harvard University, and an extraordinary thinker in a wide variety of ways, published this book about 10 years ago called Consilience, where he made a valiant attempt to show that there are common features of knowledge. There are features of knowledge that are common to virtually every intellectual pursuit. And he proposed the idea that there will be this, by understanding and achieving a common language, there will be this great consilience, that he called it, of ideas that will promote growth. I personally think that this is an excellent idea, and that by exchanging ideas across the academic silos, we can achieve a lot. Raymond Kurzweil, who is nominally at MIT, but he's really at the University of Raymond Kurzweil, is a spectacular thinker who is responsible for things as diverse as the optical character reader and flatbed scanner, as well as the keyboard synthesizer, promotes this idea called the singularity. And this is taken from his book called The Singularity is Near, which is a roughly 75-page book squeezed into 700 pages. But it's a good read. It's a fast read. And what he promotes is this idea of evolution, where eventually technology and the biological sciences join together, and this wonderful era occurs, epoch number 6, where the universe wakes up and we understand all is revealed unto us. Dr. Kurzweil believes, in fact, that we're probably in the epoch 3 to 4 right right now, and that Epoch 4 to 5 will occur in 2020. So I would dare say that we're all going to be around to see it. The last driver I want to talk about very briefly is which is called personalized medicine, which is the idea that I know your genes, therefore I know you. We know right now that this is patently false. Genetics is not destiny. There are many aspects of human existence that are determined by post-translational modifications and not by the actual writ large version of the chromosome. And so therefore there's a social version of personalized medicine, one that I personally subscribe to, which is that personalized medicine is the right health care to the right person at the right time, and one might even say at the right cost, so that at the cost that a society can bear. So anyway, my short 10 minutes of fame introduction, I would like to just again welcome you to the Texas Medical Center. I can't say on behalf of all the institutions here because they're so siloed, they don't know whether they're supporting this or not. But again, you know, the Texan worldview is a very different one from those of other civilized, and I'd say we use the term loosely, other civilized societies. And I think you'll get appreciation for the slightly bizarre culture in which I live over the next 2 days. Jack?
Thank you very much, Cliff. So my name is Jack Poe, and I am the program chair for this conference. And I would just like to briefly go over the program for today, and we'll have a similar session tomorrow to talk about the program tomorrow. So there is an active Twitter hashtag in case you guys want to use Twitter. So just very quickly going over the program, right after these introductory remarks, we'll have a keynote speaker, Matt, and we'll have then the IDEO session, some track sessions, and then a number of sessions after that. And I will talk about them more specifically here. So Matt, who is the Dean of Engineering at University of Washington, will talk about, is molecular imaging truly needed to translate the promise of molecular medicine into a clinical reality? After that, we'll have the IDEO introduction session, where session is spelled incorrectly. But IDEO this session will actually be open for all the attendees of the conference, and they wanted us to remind you guys to please bring your wallet, and they promise not to take any money from it. After that, we have 2 track sessions. One is on commercialization. The other are oral presentations of submitted abstracts, and one is on imaging. And then immediately afterwards, we have the Space Medicine Roundtable, which is moderated by our student organizers. So there is a 15-minute break between the track sessions and the Space Medicine Roundtable. So we've arranged for boxed lunches that are pre-packaged, and there's a separate checkout line if you decide to get it at the Blue Water Cafe at the Methodist Hospital. So we've only ordered 50 of these boxed lunches. So if you're interested in attending this session on time, please go over there immediately after the track session finishes and buy the lunch and come back. So after that, we have 3 more track sessions. We have imaging, global health, and we have a student-led innovations that online only shows 2 sessions, but that's because we have 2 special groups of invitees. So Jennifer Keller-Jackson from NCIA, which is one of the sponsors for this conference, will actually talk about their new E-Team grant program. So they are a nonprofit focused on promoting entrepreneurship among students and fellows. So they have this new program where they're competitively giving away $100,000 to multiple teams of trainees every year to get them to start up their projects and potentially turn them into companies. And then we have 2 special people, Haley and Greg, who will talk about their experiences bringing a student, essentially a student-driven innovation from MIT into the developing world, and their company right now is called Autoclave. And then we have another track session, new applications also happening at the same time. And then Rick Valencia from Qualcomm and the X Prize Tricorder Prize will talk about their $10 million challenge that has sort of gotten a lot of news recently. And then afterwards, we'll have the Global Health Keynote panel, which is being moderated by Matt Dashiell. And we have 1 substitution. If you guys looked at the program, Melissa unfortunately had a family emergency and won't be able to make it, and Ben will be on this panel in her place. We have a poster session afterwards where appetizers will be served. Just one note that Cliff wanted me to mention. So as many of you have noticed, this building is a hospital building. It is not a major patient care area, but there might be patients walking around. So please be very mindful of any clinical activities and any patients who you might bump into in the hallways. So the IDEO Workshop, IDEO's team will talk more about it at their session, but one thing I wanted to mention is the specialized IDEO design challenge teams themselves will be working throughout the entire conference and actually through the night on their work, and they will report back tomorrow. All the attendees are actually welcome to drop by their room, which will be open for you guys if you guys want to just pop in and see what's going on and give advice to any of the teams. There will actually be snacks, so we have a sort of junk food in that room throughout the entire session, so deep into the night, so you guys can go and see what they're doing at any time. So now I'm going to turn this over to Srini, who is our theme chair for commercialization, who will introduce our major keynote speaker.
Good morning. It is indeed my honor to be introducing Matt O'Donnell at this conference. I was just texting my wife a little while ago, and I said, I have to go introduce Matt, and she said, you just have to say, Matt's cool. That's probably the best introduction that I can give him. And you can obviously read all of his accomplishments down there, but I want to highlight just two things. I think Matt brings a wealth of experience. Right around the Jurassic era, he got his PhD, but if you look at him, he looks like a graduate student or a postdoctoral researcher, but he has a wealth of experience. Did about 10 odd years or so in GE as a research engineer, and then spent the rest of his time in academics. He's been an endowed professor at University of Michigan, following which he was the chair of the Bioengineering Department, and now he's the dean of engineering at University of Washington. And not just the experience, the output has been phenomenal too. What I was told here on this was 50 patents and over 200 publications, and he was just telling me this is 10 years old at least. So you can extrapolate from that what his output has been phenomenal. So we are truly honored that he's here to kick off this meeting. Matt.
Thanks a lot. Well, this is an interesting concept for a conference. I'd love to see how this is going to go over the next couple of days. I love the IDEO folks being here. I've done a number of things with them, but not in the medical arena, which is my own area. So it'll be interesting to see how they approach that. But today what I wanted to do is I want to set the stage by talking about translational research. And I'm going to do it in a couple of ways. I want to define from an engineer's point of view, because I know Al, tomorrow, right, you're going to give a talk which is more from a clinician's point of view, but do it through some examples. So I'll have an example, two of which are, I would consider modest successes, and then the third, which is the title, is posing where we are right now with a particular technology and what do we need to do to actually translate this into the promise that we all hope will help us to deliver molecular medicine. So translational research. So this is my own personal, not definition, but points, which I think you have to take into context when looking at translational problems. First of all is a technology push. That is, from an engineer's point of view, you come up with something cool, right? Could be a new device, could be a new molecule, could be a new software or system. And you think that it's going to solve some major medical problems. And so you're going to try to push that technology into clinical applications. And there's examples of success stories. I think a lot of students get told you can't do it this way. No, you can do it this way, all right? But it has to be the right circumstances. The second is a clinical pull, and that's kind of the obvious one. You go talk to physicians, you find out what is a clinical need, you adapt technologies to that clinical need and deliver it to the hospital. And I'll talk about an example of that and some of the limitations that you actually have by focusing exclusively on clinical pull. A key point that's common to both the technology push and the clinical pull is there's got to be real application out there. Even if it's a technology push, you ultimately have to say there is a specific medical problem, biomedical problem, which you're going to go after. And then finally, at least in the Western world, and I predict this will be true as we really push, as we're successful on global health throughout the world, is that the commercial implementation is almost required to bring anything to scale in the clinic. And so you have to be mindful of that from the beginning. So technology push, clinical pull are the two methodologies usually for bringing technologies into the clinic, focused on some specific application ultimately, doesn't have to be in the beginning, but ultimately, and then delivering it as a product in some form of the pieces. So let me go through the technology push first and use an example. First, in technology push is usually the clinical application is pretty well defined. Okay? Something is already out there and is existing. But there are technological limitations which are apparent. That is, the way in which the current standard of care is delivered has some severe limitations. A disruptive technology is emerging. Okay? Something that didn't exist when that standard of care was developed is coming online. And I think this is a key point to be thinking about this as you're looking in these areas, especially, is a commercial path is likely. That is, there's got to be a way to do it, right? If you have to develop a whole new business sector, multiple component, complex business sector to bring this new technology to bear, it's a very, very difficult road to build. Okay, so let me give you an example. And so the example on a technology push comes from an area I worked on about 20 years ago, which is IVUS, or intravascular ultrasound. And the principle was a very, very simple principle, which was the disruptive technology. And that is, the state-of-the-art at the time, about 20 years ago, is if you wanted to stick an imaging system inside of somebody's artery, and primarily coronary arteries for intravascular ultrasound, is you made a little crystal and you mechanically scanned it. And the reason you did that is because this had to be a disposable device which had to be manufactured for a couple $100 to meet the clinical need. So the systems that were developed at that time met that need to a certain level, but also were cost-effective in delivering that. At about that time, around 20 years ago, there were technologies coming out in conventional ultrasound which levered the principle of phased array. So this technology was coming, but it was nowhere near appropriate in scale or cost to what you had to do in the catheter device. However, if you could, it really could dramatically change the way in which this technology was used clinically, and that's what I'm going to go through. So it's this idea that instead of doing a standard phased array, we came up with an idea of doing what's called a synthetic phased array. And the reason we could do that is because this geometrically was in this very, very small area, so we could go very fast. We could go almost 100 times faster than a conventional ultrasound machine. So we traded off that speed with a way of making the electronics and the array very, very simple. And it was so simple that, in fact, you could be integrated onto a single catheter. So this, as the single element transducer of that era, of the late 80s, early 90s, we were going to be replaced with a 64-element array transducer. So this is a technology push, right? We're taking that kind of and trying to bring it to bear. Because we used this synthetic approach where we could use time, trade off time with complexity in terms of electronics, is we could fully integrate the electronics into the head of that transducer. There's no, it's all there. The front electronics is all in the catheter. And we used processing back in the console, which allowed us to make up for this simplicity and actually gave us fairly good images. So here's, again, a picture of the technology. This was the state of the art circa 20 years ago, which is a single element transducer, which is a mechanically rotated and delivered over a guide wire into a coronary artery. Typical dimensions here, this is 3 French or so devices, so it's a millimeter scale devices. So this was replaced with this, which is these 64 elements now delivered over the guide wire So it went through right as a donut, right through the middle, so there was no image artifacts. And all the electronics driving that were integrated into the front end. So this is pure, this is take advantage of the semiconductor revolution, pushed all this down into the front end. But the trick we had was making this electronics here not look like a standard ultrasound machine, be very, very simple, because we took advantage of time, because we could go very fast versus complexity. Here it is. Oh, there's 1991. That does date this. So that is the device. That's this, just with a shield outside, and that's the full electronics for the system. It's that little guy. So it's mounted on a three French device. Makes pretty good pictures. So just to calibrate you here, these are ultrasound pictures, a little underexposed, but ultrasound pictures where this total dimension here is 10 millimeters. And you're looking from the inside out, so this is delivered to a coronary artery. When you see these little dots going around like that, I know a cardiologist here will know what that is, but for you out there is stents. So this is very much now can be integrated very closely with the whole stenting, stent delivery, stent deployment, and characterization of the delivery depth. But you can also do things like very easy see calcifications, very easy see eccentric plaques. You can make pretty high resolution, typically in over about 100 micron resolution images with this very simple device. Under $200 to manufacture, disposable devices. Okay, now, technology push as opposed to going to clinical pull. That all sounds fine to us. So why do we think this is totally disruptive? Well, it's disruptive, but if you look at these pictures that we had here, they were about the same as what you got with that little mechanical scanner. So why? Why go through that huge type? Because of disruption. Once you have a technology in place which you know is disruptive, then you can do other things that the other guys can't do, that if it can have clinical value, can totally change the game. And here is that case. So there was multiple things that you can do with an array that you can't do with a wobbling single element transducer. And so I'll give you one of these, but there's a host of these that can be done. And one of those is real-time blood flow imaging while you're in situ, while you're inside a coronary artery. Okay? And it's an interesting geometry because you can't do Doppler, okay, which is a normal blood flow imaging system. It has a Doppler effect where the motion is along or against the propagating beam. So I'll show you just in a second. You're exactly orthogonal in this geometry. But because you have arrays, you can do some decorrelation measures. That is, you can watch blood as it goes by and watch the change in the image characteristics as it goes by to quantify flow. And because it's an array, you can do real-time estimation with that. Can a mechanical scanner do any of this? No, because it's moving. It's physically moving while the blood is flowing. So you don't know when you see a relative motion. You don't know whether it's a transducer wobble or a slight imperfection in the transducer wobble or a blood flow. Here, it's all done electronically because you have the array. So here's that geometry. You have an array which is side-looking and the blood flowing going this way. But there are standard signal processing tricks that you can do with this using filter banks and decorrelation processing to notice the changes and actually quantify the changes that you have in blood flow. This is a first image from about 95 or 96 where we just superimposed an estimate of the blood flow velocity in here. This is actually an ephemeral artery of a pig, I believe, showing here, but there's a color encoding between velocity, just like you would have in a Doppler scanner, but there's no Doppler processing. But this is done with this array, which is shown right here and looking out. So you provided something that's radically different than what the previous technology could do. The technology push is delivering it at a cost and the size, integrated that's identical to what the market currently was. And how was it used? Well, it was used in what eventually became a product called ChromaFlow. And these are a little underexposed, and I apologize for that. But what you could do then is make images of the blood flow simultaneous with doing cross-sectional conventional ultrasound pictures while you're performing a procedure in the cath lab. And where was that become interesting was in stent deployment. And there were multiple devices that were built during the time. One was which is still, you can still buy commercially, although it's not used as much recently, but that is, it's an integrated device which has imaging and the stent delivery, and the stent delivery balloon on it. So it's a singular device that's on there, or you can use them as independent devices. But you do things like this. That is while you're imaging and you see those stent struts out there, you want to know if that stent is opposed to the wall. You want to know if the stent is really providing the new blood flow, or reintroducing the blood flow into areas where there's a blockage. And so what you want to see is, you want to see between the array and where the stent struts are, you want to make sure that flow is fully recovered. And this is a way in real time that you're able to see that and deliver that. This is just one of about 5 additional features that the array system adds to this situation, yet it provides the same quality of the images that are out there. So this is a technology push, right? See an application. The application is very well defined. Intravascular ultrasound to guide percutaneous procedures in the coronaries. Okay, very, very well-known applications. You see something that can be disruptive because it can replace what's already out there, but then in so doing adds significant value by adding significant extra features. The commercialization of this was done as a collaboration between my old lab at the University of Michigan, which is the Biomedical Ultrasonics lab in the Biomedical Engineering Department, and Endosonics, which is a company out in California, which were starting to try to bring ultrasound into catheter-based devices and trying to make really the first disposable devices for this. I don't have to disclose any financial interest here because they no longer exist. And so I have no financial interest in anybody anymore, but there's now morphed 2 times, bought, big fish eating little fish, getting eaten by bigger fish. And for those of you who know, the company's called Volcano Therapeutics, is that their core technology is this technology that was started to be developed about 20 years ago. Okay, so a very strong commercialization partner to bring this thing to the clinic. Okay, so just looking at your faces, I think you get the idea of this. They're pushing it in, looking for ways to enhance what's already out to state-of-the-art, well-defined clinical need, and a path for commercialization that was fairly straightforward for doing this. Okay, so let's do a second example, which is a clinical pull. And so on this one, the technical need is not often well-defined. Okay? Somebody has a problem. What I always love, by the way, for students out there, I have this bioengineer's credo. So physicians, please close your ears. But this is from an engineer's perspective. I always said is, you want to be in the clinic all the time. You want to go talk to the physicians who are actually delivering clinical care. Listen to what they say they need. You listen to what they say they want, but then give them what they need. Okay? And so this is exactly that. The clinical pull is one, is you really have to hear what's going on out there. But the technical need, because again, my engineers and physicians have a very similar thing. If you ask them their problems, they'll tell you the solution. Right? So what you really want to know is what's the problem, because often in the clinical pull is the technical need is not well defined, or else there probably would have been a solution already. You must shape, this is one of my little credos that old grad students and postdocs of mine get sick of when they hear this, but you must shape the clinical question in a way that can be resolved by technology, or else as bioengineers we shouldn't be in it. Somebody else should be in it. Resolved by technology could be a new software package or a new system, a new delivery system. But if it's not posed in a way it can be resolved by technology, then it's really not in our scope. And the last point on this one is that because the technical need is not often well defined, the best technical approach is usually not the first technical approach. That is, you start to work on something in this area as approach, and you find out things along the way, and so you will be changing as you go, and that makes commercialization difficult, because in business, anything that has to do with uncertainty always is something that's avoided in commercial development. You try to minimize uncertainty, minimize risk for commercial development, yet often in a clinical pull situation, you're making it difficult because you're maximizing your uncertainty. You're changing things a lot as you go. Okay, so let's do an example. And this is an example which is still in progress, but the research started nearly 20 years ago and has been starting to go clinical over the last decade. And so the technology is related to functional assessment of cardiac contractility using imaging, but in fact using a technique called Speckle tracking within ultrasound. And I'll explain what that is as we go. So this really started, I would say, as a technical push or technology push. That is, this idea of trying to use imaging and tracking of images to look at deformations and look at mechanical function has been going on, like I said, for about 20 years. But the clinical pole, what I want to talk about is a specific example within the last decade of trying to say, can you really measure viability? And in fact, the specific clinical application I'm talking about here will be focused on stress echo. All right? And for those of you who are not familiar with that, is the idea is taking a stress test to look at cardiac function. It can be done either physically or it can be induced biochemically. But it puts your heart under stress. And so what you're looking at then is trying to make functional measurements, some kind of functional measurements of the heart between the difference of a resting state and a stressed state to look at performance. And one of the holy grails in this has been trying to use imaging to analyze the differences you have. And the motivation for doing that is you can save cardiac catheterization. The standard of care is, when in doubt, send them into the cath lab to measure performance. And so the idea with the stress echo is to try to dramatically reduce, using this technology for stress echoes to try to dramatically reduce the number of people who will be catheterized. Okay, so let me give you a few slides and just give you background of the technology and then talk about this specifically for stress echo and how is it an example of a clinical pole. So first, the technology. And so some model system studies from a number of years ago. This is just a Langendorf prep that was used to look at, in a very, very controlled way, can you use ultrasound to measure contractility or imaging in general, but in this case it's all ultrasound for measuring contractile function of the heart. And so this beating heart goes into an imaging setup for doing that. Okay, and just a simple thing you will do as a modulation, rather than trying to do a stress, no stress, is we do a full occlusion. So we have a full ischemia that's induced in the localized region by taking the LED. And then we'll show an imaging plane. Everything will be a specific imaging plane where we're going to have some acute ischemia involving. And this is just an experimental geometry. So you could be looking at cross-sectionally through a short axis of the heart. So you see the left ventricle and then the right ventricle to the side. And we had a couple of probes that were looking at this. Okay, so I'm going to give you a clinical test on the next slide. So let me set you up for that, and you can't answer over here. Okay, so a clinical test on the next slide. What we have here is after ligation, it's showing you two images. These two images are the same. They're just looking at the image from a different point of view. It's a technical issue which has to do with the ultrasound propagation direction. So it is all the same object in the same view, just one is from one transducer, one is from another. On the left side is before the ligation. On the right side is after the ligation. And the likely site, based on just the geometry of where the occlusion is, the likely site for potential disruption and ischemia is in this zone of the left ventricle, in the anterior zone of the left ventricle. Okay? So on the next slide, you're supposed to look at these echoes, and you're supposed to tell me whether that region over here is functioning properly compared to what's happening over here. Anybody under the age of 40 want to make a guess? Yeah, go for it. I love your courage. Go ahead. Slightly? Yeah, it's very subtle. There is. Al, can you see it? Yeah, he's just, that's the That's why I didn't ask him. Yeah, you can see it. But it's very subtle what's going on. Can you quantify it? Do you know exactly the region? Do you know how much of a loss there is? It's very, very hard to do, okay? Oh, I have the power. That's right. Okay? So yes, there is some abnormal motion. You know, a clinically trained cardiologist from a major research institution that just suffered a hurricane damage is able to do that. But it is a very, very hard thing, and it's very, very hard to be reproducible. And remember, your decision is, do I send them to the cath lab or do I send them home? Right? If you send them home, medical consequences can be extreme. If you send them to the cath lab, it's a lot of bucks. Okay? And you're going to do it based on that. You have confidence, though. I know Al. He would have confidence in being able to make that decision. But it's very, very hard to do in a standard clinical setting. Okay. So with that background, what we've looked at, like I said, for a long time, is using imaging systems to actually image the strains or the mechanical deformations or the rate at which they change, as was insightful talked about here in the answer, to do that. And the idea is, of course, the most simplistic idea in 1D, if you have two springs and one's hard and one's soft, you put a constant displacement on there, is that most of the displacement will be soaked up in the soft material and less in the hard material. So if you can make a measure of the displacement point by point by point and take a spatial derivative, you have something which is directly related to the mechanical characteristics of the material. Okay, so how do you do that in an imaging system? You do that in an imaging system. Here is a very simple demonstration. This is actually ex vivo, and that's a kidney, not a heart, but it's a cross-section through a kidney, just embedded within the phantom. But you can think about it in terms of a very simple deformation and trying to track a deformation within tissue. Here is before you apply an external deformation. Here's afterwards. You can tell there's a deformation because you can see that the bottom has been compressed before and after. So you've done the compression of this guy by forcing down on this. Okay. If you had this and you said, I just want to get a characteristic, a mechanical characteristic of this object, this large object here, which is the kidney, is that I would look at the total dimension of this object before applying the displacement. I'd look at it afterwards. And the strain is simply defined as the difference in that dimension normalized to the original difference. So it's a compression in this case. If I could actually image and look along this thing, if this was a uniform object, it obviously isn't, but if it were a uniform object, I would see a displacement which would just linearly scale with the distance as I went in. As I pushed this thing, each piece was pushed and its neighbor a little bit more than its neighbor. So if I looked at the slope of that, again, this derivative, the derivative, that will tell me the strain. What happens, though, if inside of this object I have an area which is significantly different? In this case, let's say it's significantly harder than the rest of the material. I do this deformation. I will not see a perfect straight line like this. What do I say? And again, this is in cartoon fashion, simplistic. It's much more complicated than this. But simplistically, what you would see would be a displacement in the soft. And once you got to that hard area, because it just displaces as a body, right? It doesn't deform. It displaces as a body because the softer materials will displace. You'll be able to see that when you take the derivative. When you take the derivative of that, you'll be able to identify the region as hard. So how can you do that with an image? Is that me? Or is it those guys drilling that said we're going to wait till 9:30? Okay. Anyway, so how do you do that with an image? You do it with an image here is Speckle. For people who are not ultrasound types, is they see all this junk in the picture. This is a uniform gel phantom. So why do you have all this speckling that's in there? That is considered noise and ugly. For ultrasound people, it's joy and beauty. And the reason being is because it's a characteristic. This doesn't flicker. This doesn't flicker at all. It's not electronic noise. It's not random. It's based on structure. It's based on microstructure. So if microstructure moves, you can use that speckle characteristic to track how that microstructure has moved. So it's actually an ideal target for being able to do tracking. And so that's what happens in an ultrasound system is you have this microstructure which interacts with the ultrasound beam, presents the speckle, and the speckle is caused by interference. You have that, but it's a structure. That interference pattern is directly related to the original structure, and as that structure moves, so too does the speckle move. And so when you do that, let's go to the simple example that I had before. Before, you will get a waveform, and this waveform is just the radio frequency. It's the scattered ultrasound wave that's coming back to a transducer along this line, because you're imaging along that line. After, you'll get a similar waveform, but what you'll notice is, if you look very carefully, is that there's a shift between, for this local, in a local region, there's a shift of the waveform in a particular direction. In fact, if you look at a region of this waveform and then search the other until you find a match, that difference in displacement is related to the displacement of the material at that point. If you do it point for point, you get an image of displacement. You take a derivative of that, you have an image of strain. Okay? So you do that by correlation tracking. That's the math. You can do it in 1D and 2D, and you do it in 3D. And if there were more D, you could do it in that too, as long as there was an appropriate diffraction pattern associated with it that's in there. And so you do these tracking and finding for the peaks, but it's all the same principle. Once you get a displacement field is not very informative, right? Because you can take an object and move it a far away, and it has nothing to do with mechanical characteristics. Mechanical characteristics are deformations. That is, the relative change in displacements, local changes, which are defined by strains, and those are given here, where U and V are in 2 dimensions are the components of the displacements. And so when you, in fact, take derivatives, you can actually see the objects based on their hardness, softness, their stiffness. Okay, so let's get to the heart. So in the heart, you can't control the deformation. Nature controls the deformation. Physiology controls the deformation. What you want to do is see if that deformation is appropriate for a proper functioning of the heart. So in this case now, you will have images where you're not controlling the deformation, but they're in real time just coming at you, and you're going to have to process them. Okay, but it's really still pretty straightforward how you do that. And that is, think of this simple case where you had the before and after, and the before and after can now be thought of, sorry, I forgot my own animation. So you can do tracking about that. However, you should now think of that deformation in a cardiac cycle is like going from frame to frame to frame to frame, time within a cardiac deformation. So as opposed to saying I'm going to look at a correlation between before a deformation or after a deformation, I'm going to look at correlations from one frame to the next frame to the next frame to the next frame in an image sequence over a cardiac cycle. You then either look at the displacements between and the strains and the change in strains with time, i.e. strain rates, or you accumulate the strains over a fixed time, such as you would have in looking at the total strains at peak systole, for example, during the contraction phase of the left ventricle. And by taking derivatives, you can get mechanical information. Okay, so that's the background. Back to the clinical need question. All right, so the clinical needs, remember we were looking at the trying to understand the difference between that ligation and looking for that one area up here, whether I could look for dysfunction in the deformation patterns. And what we have here, just showing here, are the accumulated displacements. This is in one component of displacement and the second component of the displacement, integrated over systole in that study. The way in which we'll present the information, though, now, is back in terms of deformations, back in terms of strains. But here, because the geometry of the heart is fairly complicated and you don't have control over the way the deformations are made, we compute the deformations in the coordinate system that the heart tells us. So it's a principal components analysis, or principal stretches, principal strains. There's lots of different phrases for this. So you're going to find where the primary deformation, direction and magnitude of the primary deformation in a local part, and there's some math, but all of it, again, goes related to these displacements that you've measured. So from those displacements, you can compute the local coordinate system. So here's the bottom line after you do that. Remember that very subtle, I'll come back to the guy who had tremendous courage, thank you very much, it was very subtle, you're trying to see this. Okay, so I'm going to play the same thing back, except here what I'm going to show is through a loop, through systole, you will see the direction of the primary deformation that evolved during systole, from all that little image processing and tracking and all that. And tell me if you can see a difference between, on this side, before ligation and after ligation. I heard a You think you could read that echo? Okay. So what you're seeing is primarily radial deformation for one of the, so you have radial and tangential, the two primaries that you have. And what you see with exactly in the point of where there's the ligation is because this is totally passive, and just for this particular geometry that you have, it's totally tangential at the time when be normal would be totally radial. Okay? So very, very straightforward that would be in there. Okay. So we were hot, right? This is about 10 years ago. We got this stuff. It's cool. Yeah, we got to go to going in and stress echo. Said, this is absolutely the place where this can be applied is in stress echo. And the way we did it, so our proposal was very simple. And that is we did a dot product between that primary deformation before somebody goes into stress and after they go into stress. Okay? Because remember, if it was going like this and it's going like this, what's your dot product? Is 0, right? If they're going like this, it's 1. So you can present a very simple 0 to 1 type of image, which tells you before and after. So if I do it to those images, focus on this one. This is just some machine artifacts we were talking about in the paper. But right here, right in that region that you visualized, you can see exactly that's where you get that dot product. So piece of cake, right? Absolutely. That was 10 years ago. Well, of course, it's not a piece of cake. I wouldn't have said it that way. So it's, deformation direction before applying the stress, deformation direction after the stress. Okay, so going to the clinic. Stress echo is very challenging. People are running. Their heart rate is up. You got somebody's contractions trying to keep this thing in place. It is a very, very challenging environment. And it's an environment that absolutely demands real-time feedback to get any kind of reasonable image data out of it. Our system, you acquired data, you waited a half hour, and you got a result, right? Which in the conventional imaging, in the radiology world, that's real-time. It's no issue. For this, we couldn't do that. We tried it, and the first few patients we tried to do, it's absolute garbage. The image quality itself for stress echo is very poor in general. The image frame rates are very, very high, so if you're trying to do correlations between frames, if you don't have very high frame rates in this stress state, you can just be totally decorrelated, and so you can't track anything that's in there. And, again, high bar for reproducibility. You're making a decision of whether this person's going to cath or home. All right? So it's a very high bar, and that means you have to have an exam that when you measure them once and they come back and you do another stress test and you measure them again, you better get the same answers if it's the same person under the same conditions. So it's very. So this was the clinical. We got this little lesson from a young faculty member in cardiology and a tech at the University of Michigan Hospital. And the tech was almost dismissive, like, you guys are smoking dope, because if you really think that you're going to have this thing that sort of, takes these very nice, high-quality images and go away for a half hour, and then you bring it back to us, that person's already home. He's on the way home. Okay? So what are we going to do? So this is a place where I think clinical, and we have nice technology things to work, but we have a clinical. How do we address the clinical need there for this? So the approach to clinical translations, the first thing we did is we said this real-time thing is a real bugger. I mean, there's just no way that it's going to be adopted. So we immediately went out and tried to find a way in which we could take what we were doing with the Speckle Tracking and do it in real time, to do it as the images were coming in there. Of limited data sets. You couldn't maybe run it for all time, but at least you could help the tech in order to get the data. So you could provide some real-time feedback. Well, we tried to do that. It's not the great thing to do in an academic setting, and so we partnered with a local company in Ann Arbor to do that. We then said we're going to use high frame rate data to drive feedback. So we're going to optimize the data acquisition. So we get in there and not use standard protocols. We're going to cheat, in effect, on the standard protocols that were done for the imaging. I'm going to trade off spatial resolution, the holy grail of what we're trying to do. Those low vectors were sub-millimeter that you're looking at. Actually, it was a couple hundred micron was the size there. But we were going to trade off the holy grail in all our publications and the like with accuracy because we had to be reproducible in the clinical environment. And finally, the dot product, when we tried to explain the dot product to a cardiologist, sorry, Al, but when we tried to explain the dot product to a cardiologist, it just didn't go over very well, okay? And so actually a former student came in with a very nice way, natural way for clinicians to be displayed information, which is effectively the dot product. Okay, oops. So this is from about 5 years ago when this Pixel Velocity was a company, was a little military contractor, but they knew how to do computation, real-time computation fast. And so this is the first machine that they built with us about 5 years ago, which just emulated what a conventional clinical strain rate imaging system does, except this is 100% in real time, and it uses that correlation engine with the high precision correlation engine. What it's led to is a product which has just been introduced. Actually, they were at AHA. So they introduced it, American Echo, I think, which was about a half year ago. The product is Echo Insight, and it's for stress echo. So it will do a full cardiac mechanical characterization based on stress echo data. It provides packages to help techs to take the data appropriately, full processing packages, and to do it. This one, I do have to say, I do have a financial interest in serving on the board of directors of this country. So you should know that, as all institutions now have to tell you that you have to disclose. And I'm not going to say any more about it because you can go off on the web and find out about this. But why I use that, why I use that as this example is that the clinical pull is really a lot different than the technical push. The technical push, we just really reproduced what was already in there and added features. The clinical pull is having something which you think would translate, but no, the clinical need of saying I have this environment in which I have to work is fundamentally different than the environment in which you develop the technology. Then you have to find technologies that address that clinical environment and, in fact, in this case, adapted it to come out with something which can be clinically useful. Okay, the last piece, should have about 20 minutes and then a lot of time for questions, I hope, is the future. So this will be current research, but I put it up as a question for what needs to be done for translation in the future. And I think this conference, actually I stole this slide a couple years ago from a study, but it sounds like this conference is going to be right on to what's happening here. And that is, they were looking at the future drivers of healthcare, both in North America as well as worldwide, and they noticed that there were three major themes that come out. Molecular and personalized medicine, you heard about that already in the opening. Access, cost, and quality of care. Boy, we're going to hear about that in global health world, right? And down here, proficient use of information, e-health, the idea of using information technologies as a glue for all of this, and tremendous overlap between all of these. What I'm going to talk about is this last example, and hopefully to open the discussion, is technology directly related to molecular and personalized medicine. Okay. So the holy grail of molecular medicine. This is our holy grail, and again, I like the introduction of saying this is it Calvinist, the predetermination? I always get the wrong. But, you know, if you know the genome, you know this person is going to do, what their SAT scores are going to be, where they're going to college, what are they going to eat, you know, I mean, which is, of course, incredibly naive. However, it's a very, very valuable data set of what's going on. So this is a pathway, and we stole this from Lee Hood out in Seattle, who talks about P4 medicine. But it is really an approach to looking at how the benefits of the molecular revolution in biomedicine can be integrated and translated into real clinical tools. So the idea is you have these multiple steps, and the multiple steps have the genomic analysis, and hopefully that leads to a rational plan of prevention of any disease states where there could be a predilection for. Using molecular screens to predict, and this is an area where Lee Hood, again, has been very, very prominent in looking at the role of that for modulating medical treatment. But when there's something that says the potential disease process going on, we're positing that molecular imaging is going to be right in the middle of that, of trying to determine what are the active metabolic pathways involved in this disease, which will then drive and help the molecular therapies, which are then applied based on the person. That is, the person's systems, not only what's predicted to happen, but with the molecular imaging, hopefully you're actually seeing the expression of what's happening. But the most important part of this, I think, in actual translation, is the feedback loops that you have. The feedback loops between when you screen can just can change prevention plans. When you do molecular imaging and see what's going on, you may not need a therapeutic intervention. You may need a different one, which gets you back into a role in which you're screening. But again, if a screen says that something's happening, you go in this. So you have a virtuous loop here where you're using this irregularly as driven by this, but this has the predictive power to tell what's going on. If you've now gone into a potential disease state where a therapy is appropriate, how do you monitor the efficacy of that therapy? You monitor the efficacy of that therapy using the molecular imaging. You have another virtuous loop here. And so I think the point, and which is what I'll make as a provocative statement to drive this discussion for the next 20 minutes or so, is that I think molecular imaging is right in the middle of this in the delivery of molecular medicine. Okay, so let me just define molecular imaging in a simple cartoon, which is, you can think of a molecular imaging system in the most simplistic way as saying something that's going to light up like a light bulb in some kind of imaging system, and something that has a biological targeting capability. All right? So, for example, you're looking at a particular membrane-bound protein with a particular epitope. You can bring in an antibody labeling to this that will be hopefully specific to that epitope, and then you have an imaging beacon which will light up in some imaging system where, if you do the job right, you can actually do a biomolecular assay, that is a counting of the target within a spatial location provided by the imaging system. Okay, so that's the simplistic view of that. So it's driven by contrast agents, so those little agents which have both an imaging component and a delivery component, and they range in scale from the about 10 nanometers or so for the simplest agents up into the several micron scale for other agents. These agents have become very, very complicated because they're usually multifunctional. That is they may have an imaging component, they have a targeting component, but they may also have a therapeutic component if they're integrated in with the therapeutic application. Everybody's in the game. You name an imaging modality, and they think that they're the winners in this, but of course there is no clinically defined protocols yet for the targeted type of molecular imaging that I've talked about. Certainly nuclear medicine is molecular in nature and is in clinical practice, but the targeted type of imaging that I'm talking about is still primarily a research idea. So what are the impediments to clinical transit? So this is, again, one I hope this conference is going to get at. What impedes this kind of vision from getting into the clinic? The first one is molecular sensitivity. If you want to do molecule counting, you've got to be able to do molecule counting. Molecule counting on the benchtop is pretty difficult. Molecule counting 10 centimeters within the body, localized from an imaging system, can be very, very exceedingly difficult. So molecular sensitivity is a major piece. Preclinical to clinical scaling. All of you, I'm sure, have seen covers of Science and Nature and popular journals where you see a little mouse glowing in a little area, and somebody says tumor, or somebody says, you know, neurodegenerative disease, or something like that. So, so there's a whole technology based on fluorescence labeling that is really not going to scale to a wide range of clinical applications, just because of the physics. It will have some clinical, no doubt it will have some clinical applications, but just because of the physics. And so there's an issue between preclinical to clinical scaling. If you can deliver medicine, it must be on humans. The agents, you know, they can be wonderfully sensitive, scale, but if they create a toxicity of themselves, then you'll never have this as a routine clinical translation. And the final one is, boy, do you see dollar signs? When I look at those things, I see dollar signs, right, all over the place. So cost will be a major driver. That's a major driver, obviously, in the developed world, especially with changes in medical delivery systems, but especially in the developing world, right? You're not going to have your portable MRI. Well, I shouldn't say that. I always make absolute statements. It would be hard to have certain types of systems be highly portable and very, very cost-effective in challenging environments. Okay, so what I'm going to argue in the next 10 minutes or so is why you can use ultrasound for molecular imaging. How and why you can use ultrasound for molecular imaging. So first of all, you have PET. This is a very complex, high-cost system. That's 1 unit human right there. So that gives you the scale of this for the radiopharmaceutical, so for the isotope separation. And then the scanners are all whole-body scanners. And beautiful molecular sensitivity, relatively poor, although getting better, admittedly getting much better, but relatively poor spatial and temporal resolution. So it's an imaging tool, not of the highest quality, but beautiful molecular sensitivity. MRI, beautiful spatial resolution, temporal resolution continuously getting better, very poor molecular sensitivity for molecular imaging. Large-scale systems. I love this because I put this picture in. I don't know who these people are or why, but I picked it off the web because I typed into Google, portable MRI system. This is what I got. Okay. So why ultrasound? Okay? So I love the tricorder challenge. I love the tricorder challenge. All right? Because from an imaging perspective, it's already there. And I think, again, this can go another generation of scaling so it can become a small component of a tricorder kind of system. Okay, when I teach, there's a class I still teach about commercialization at UW, and I ask everybody, anybody know who that is? Oh my God, you pass. Nobody in my class of 50 kids, junior and senior undergraduates last year, knew who that was. Okay. It's Jeff Immel is the CEO of GE. And that's a GE product. And it had nothing to do with this. I don't have to disclose anything. But this is why? Low cost, non-radiation, non-invasive, highly portable. This guy works off a battery. And fundamentally real time. Guidance, in the field use, wonderful. But what does it have to do with molecular imaging? Okay. Well, people have tried it. And actually, there is a body of work, or probably over the last decade, of using molecular imaging where the contrast agent fits this little rubric. The little rubric is you have a targeting agent. So I here have this cartoon of an antibody targeting to a membrane-bound protein, a linker, but then your image beacon, and this is not to scale. So it's several orders of magnitude larger than what you need for the biological piece, because that's what you need to see in an ultrasound system. That's a microbubble, typically 1-2 microns in diameter. This has been used, but it's primarily been used for some very simple approaches in the vascular system, where you can get this size of an agent in. Extravasating this and bringing it in for cellular, let alone intracellular processes, is really outside the realm of this technology. So ultrasound really has not been a player in molecular imaging to date. But can it be? I think the answer is yes, and there's, over the last decade, an evolving research area which combines light and sound, but at a molecular scale. And it goes under the rubric of photoacoustics or optoacoustics. You'll hear both names for that. And here's the idea. Whoops, I'll go back. So let's just do a quick Gedanken experiment. Imagine you have an object that embedded within it has a perfect optical absorber and everything else is transparent. Okay? If I bring in a laser pulse, which will have a spatially, just a plane wave illumination of this object, but I temporally modulate, i.e. bring a pulse, then this region as a perfect absorber will absorb heat. The time modulation, so that means it will thermally expand. The time modulation of that by the pulse laser presents a time modulated expansion. That's acoustics. That's a pressure wave. So from this, there'll be a pressure wave that can come off, which can be detected by a conventional ultrasound detector, and you use the ultrasound detector, just like you do in conventional ultrasound, to reconstruct the source of that absorbed light. There's a beautiful wave equation, so a simple wave equation, which is related to the heat absorbed and the coefficient of thermal expansion that's in there. When you actually measure it, you get measurable signals from temperature rises, which are fractions of a degree Kelvin, so no long-term thermal effects associated with it. And what's very interesting about it is it's an ultrasound imaging system, you're measuring that, but the contrast is optical absorption. Okay? And optics can work at the molecular scale. So systems, this is one of my former guys who's now at UT Austin, built one of the first real-time systems which integrated photoacoustics with ultrasound in there. And it's really just an ultrasound system with a little light pipes delivering a pulse laser source. So you have your box, looks like this. The probe itself is almost identical to what you have. Very simple addition to this and can be in a highly portable system. The way in which we do the imaging, and this again is kind of underexposed, but the way we typically present the images is like I did in that original cartoon, is you make real-time images with ultrasound. Interleaved with the ultrasound, you're pinging a laser, and with each laser ping, you can reconstruct a photoacoustic image, and we'll paint that on top in color to show, in a case, a distribution of molecules when you use a photoacoustic contrast agent. So that's shown here, where because it's optical absorption, you get down to the size scale that's in there. So you're down at the nanometer range again by using that contrast agent. Those contrast agents can be both extracellular and intracellular. A very wonderful set of papers from UT Austin and collaborators from one of the, I think from the Cancer Institute, MD Anderson here, of showing what you can do with photoacoustic contrast agents which go in intracellular. And they have you can actually see them going from compartments, from endosome to lysosome, et cetera, because the packing density changes their characteristics. So you're really in this molecular world. Okay? These agents have characteristics. This is not too much. Here's an example just of how you can use these things. So here's a very, very simple example out of my lab from about 7 or 8 years ago, which is, so you get an agent now, so it has this simple photoacoustic contrast with a linker, and here it's just to an antibody, the intracellular adhesion molecule, which is dramatically overexpressed during acute inflammation. So the idea is, could you image the molecular process of acute inflammation using an ultrasound scanner? All right? And so that's done up here. It was a little rabbit model of a laser-induced injury. And there's our little guy there getting imaged in real time. And this is the type of picture you get. So you have the ultrasound picture in the background, and on top of it is showing the photoacoustic image. And we just used a simple thresholding in this case, is to show the region in which there was an acute inflammation. This was imaged in real time, and you're seeing the accumulation of about a 20-minute scan that was in there. Okay? So very interesting technology, but the impact. Could it be? Could it guide intravascular procedures? 1.5 million intravascular procedures. Could you see evolving inflammation during a procedure because of your procedure in real time? That's a question. I just see my time because I want to have some discussion. So this is, there are limitations to this technology, though, and all molecular imaging has a major limitation, which is background. Okay? So here is a rat tumor, a rabbit tumor, a thigh model of a tumor where it has a contrast agent, and they're showing the photoacoustics in green over top of the B scan. And you can see the tumor right here. It's very, very nice that you can see this highlighting of where the tumor was. However, you can see all kinds of stuff before you ever injected the contrast agent. Okay, and the reason is because blood is a wonderful source of photoacoustic signal. Okay? So the way we have gotten around this is to leverage this link to multifunctional contrast agents. And the particular case we have done is one in which we use a magnetic component and a absorbing component, so a plasmonic gold thin shell for absorbing, but have isolated it from magnetic components so that we have a multifunctional approach to this. This allows us, and I'm not going to go through this because of time, but this allows us to get rid of background signals which have nothing to do with magnetism. I'll give you the 3-second version. 3-second version is I have an image and I have 2 spots, right? One spot is because of blood. The other spot's because of the particles, which have this low magnetism. I put it on a magnetic field and I start shaking a time varying with that. The guys that have the magnetic part are shaking. The guys that have the blood don't shake. Okay? So that means if I do some kind of filtering that's related to the shaking, I can get rid of the ones that don't. And in fact, if you do it right, they can be right on top of each other. And you can get rid of the one that wasn't shaking. Okay? It's a Doppler. It's a Doppler effect. But you control the Doppler effect. Anyway, that's enough so I can move on. So the questions on clinical translation here is, can a multifunctional molecular systems leveraging the cost effectiveness of ultrasound enable molecular medicine? Is this a technology push or a clinical pull? Who knows? We're at the stage now where we could try to push into certain applications, and we are talking to clinics. So we looked at the clinical application to test. Specific clinical application was the detection of rare circulating tumor cells in the peripheral vasculature. Over 90% of cancer deaths have to do with complications of metastasis. Yet there is no non-invasive tool, routine non-invasive tool that can identify metastasis until they're in the very late stage. Okay? So what we have looked at is, can you detect circulating tumor cells? This is a huge challenge. The reason being is in a typical evolving tumor, active tumor, there's only about 1 to 10 CTCs per milliliter of blood. Needle in a haystack. So what we came as approach, this multifunctional approach, is the magnetic part, which we did with the shaking and to get rid of the blood signal and all that. Can we also exploit that to accumulate cells as they're passing through in the peripheral vessel? Signal is masked, that's what I said, we can get rid of that. Okay, so here's a couple slides, and then we'll get to the conclusion. A couple slides is we made one of these multifunctional particles. We attach it here. We use the HeLa cell model. We've also done it to prostate cancer cell model in there. And here's the one thing I do want to show, which is that. So this is the one experiment, and this will just give you an idea. Can you potentially deliver molecular medicine? What you have here is a flow system. You're seeing the ultrasound in real time. You will in real time behind it. And the color will be the photoacoustic signal. As the flow goes through here, goes to the left, is a cell solution. So there's the tagged cells are in there. You'll see it at time t equals 0 as this movie plays, is the magnetic trapping system is turned on, and you'll see a slight artifact in the image as a result of that. What you're going to watch is how we're trapping the cells, and can we see the trapping of those cells. Okay, oh, let me put it here. Then I'll sum up so we have some time. Okay, so watch at t equals 0. You'll see the artifact down here because you turn the magnet system on, which has a mechanical part to it. So you see a little something that. And then you'll start to see the accumulation. Why near a tube boundary? Any students? It's the slowest flow, easiest place to trap. Okay? Then when we pull this magnet away, pew, these guys will wash out. So you are actually trapping. You're not sticking or anything. That's a mechanical, that's a magnetic trap. Okay. We've done the test. It's highly specific. This is just control studies saying it's highly specific. Here's the last thing I'm going to show you, and then we'll pose the questions to do a 10 or 15 minutes of discussion. So the question was, okay, this is all cool, but this goal is we got to get down at the level that we can see 1 cell per milliliter. So we've just done a tabletop experiment. We're now starting to move towards preclinical studies of this, of trying to see if we could detect at this scale. I guess I can do it this way. Okay, so what we've done is we put a fixed number of cells. So there's 480 cells in a very fairly significant volume, which would just flow through this tube once, no recirculation, and see how well do we do. How many cells, first of all, can we see them? And second of all, how many cells can we trap? And so as we flow through, whoop, we missed a few, but we got. Okay, so can we see that? And so that's the same type of movie. Okay, so flowing through, and you'll start to see the identification of the cells. You start picking them up. Up, and so you can see them. And so you can do a counting curve, so we can actually count the cells, and we do count the cells, and we saw 2/3, so 320 cells we can see. 1 cell per ml, easily detectable. All right, so moving towards translation, to sum up. Integrating real-time ultrasound and photoacoustics, as you've seen at least conceptually, is relatively simple. The magnet system, I made a challenge, and we wrote our NIH grant on this, as I was able to put this line in the grant, is the dollar store. Is our magnet system was all parts from the dollar store to do it. Very simple. Don't think MRI. Think of something you can stick in a little cuff. That's kind of the vision of where it's going. Whoops. So target in small amount going, and then re-engineering the molecular agent to potential toxicity. That agent that I showed you has no short-term toxicity, but is accumulated in the liver. And so there's a question about long-term toxicity. So if you're going towards clinical translation, we have to re-engineer that agent. And that's going to be a critical part of delivery in molecular medicine, is to make sure that the agents themselves don't have toxicity. So can this be a piece? Well, hopefully what I've just said is if you do this right, you are going to have a tool that once you say there's the potential of a evolving tumor, you can immediately monitor if there are any cells of a particular type. As long as you've identified the cell type, you could then target to that, because you don't have to have absolute specificity. You just have to have enough specificity that differentially you can trap them. So it doesn't have to be absolute specificity. But then you can look at this in real time, see them, accumulate them. You could actually treat, but that means you'd have to wear something like a cuff all the time. But even if it's just monitoring, then looking at molecular therapy, a chemotherapeutic, a targeted chemotherapeutic going after that, you can tell, are you doing your job for the piece of cancer which represents 90% of the morbidity. Okay, so this is what I'm going to end with, molecular imaging translation. So I just gave that example, a little bit longer than I hoped, but anyway, an example of how molecular imaging could be a driver in the actual delivery of molecular medicine, okay? And in this case, the delivery of molecular medicine is for those early-stage tumors where you have targeted delivery systems to go after them. Can cost-effective molecular imaging be delivered to the clinic? I'm not just talking about North America, I'm talking worldwide. Can the promise of molecular medicine, not only with lab on a chip or lab on a whatever kinds of diagnostics, but also real-time imaging be delivered, and molecular imaging be delivered in a way which is cost-effective, and it's in there. And this is the key question, I think, that always comes when you're at this state in something. What's the killer app? Unfortunately, killer apps probably better to talk about in software than it is to talk about in medicine. But the idea is, what application will drive this? Will it be this CTC, detection and management of metastases? Will it be something related to blood oxygenation, which photoacoustics and ultrasound is very good? It's not clear what it's going to be, but that's what we have to do. So how should we approach the translation of molecular imaging to test whether it can do this? And I think that's a question I've posed here in the specifics of molecular imaging, but I think it's something we generally should be questioning as we go through this conference over the next couple of days, is what do you have to do to translate? How do you get this so it's widespread adoption? That's the piece, the scaling is the piece I think we always get lost on, both in global health discussions as well as new technologies in the developed world, is how can you get widespread adoption, not just at the major medical centers or a specific clinic in Tanzania that your university happens to have a relationship with, but measure widespread. Okay, I think I'll end there, and hopefully we've got a few minutes for some questions.